Hello and welcome back to the CMTEQ Engineering Podcast, where we talk about all things electrical engineering, technology trends, and the systems that keep our modern world powered. I'm Chad, your host, and in today's episode, we're going deep into the topic that's revolutionizing how power grids operate, and that is the SCADA systems, smart meters, demand response, and the communication networks that actually make the grid smart grid systems, right? So as we all know, the traditional power grid was designed for a one-way flow of electricity, basically a one-way street. That is from large centralized power plants like your coal-fired power plant and straight to you guys, to us, the consumers. But as we know that in today's world, with renewable energy sources, electric vehicles, and increasing energy demand, so we cannot emphasize this point enough, there is a high increase in energy demand. Just think about the large models, the AI models, that's how power hungry they are, the data centers, right? So that basically means the old model isn't enough anymore. So we need grids that are flexible, self-healing, and intelligent. And that's where these technologies come into play. So let's begin by asking a very simple question. What is a SCADA system? So basically, what does SCADA stand for? That is SCADA. What does it stand for? So basically, in simple terms, or the definition of SCADA, it is a supervisory control and data acquisition system, which basically means it's a system that can control and store data and recommend actions in simple terms. So the SCADA system is the brain of modern power systems, right? It's basically a combination of hardware and software used to monitor data, gather informations, and process them in real time. All kind of data across the grids. So you can just imagine the type of data, right? So if you want to put it into perspective, the SCADA system will execute about 3 tasks, right? It will collect data from substations, transformers, and other assets like current transformers, voltage transformers, relays, and other devices, right? Now, these informations allows the operators to then remotely control switches, circuit breakers, and relays, right? And also, it then provides a centralized view of the entire system. These will then include your alarms and faults and performance metrics of how the power systems is basically performing. We can think of it as the SCADA system architecture will consist of number one, a remote terminal unit. So that's what we call as the RTU. Right? Now, these are out in the fields, right? That's why there is a word remote, so they are deployed. Then they collect data from sensors and sending control signal to equipment, right? Then number 2 is a programmable logic controller, so that's the famous PLCs, right? These are often used in substations for automation's task to basically set a logic that will automatically control certain things. And number 3, that will be your communication infrastructure, so which will include fiber optics, wireless links, or even power line communications, and that's also known as PLC, but not the PLC of the programmable logic controllers, but PLC of the power line communication. Now, this is to transmit data. This is quite one of a major field in power systems, studying the power line communications. So lastly, the number 4, that will be the master stations or the control center. Now this is where operators, they basically sit and visualize the grid, how things are happening in real time. Okay, so we saw the SCADA grid operators, they will be basically flying blind, right? They want no much of what's going on. Okay, so that's the old systems. So it's a SCADA that basically enable real-time situational awareness, automated fault detection, and even remote recovery actions. So that basically, in a nutshell, what a SCADA system is. Now let's elaborate more about the smart meters, which also form part of the SCADA systems. Right, so this is really a key player in modernizing our power grids, smart meters. So at the core of smart meters are basically advanced digital versions of the traditional electricity meters that usually simply record how much energy you consume over a billing period. But smart meters take these several steps further. Okay, they continuously measure energy usage and communicate that data back to the grid in real time, or maybe we can say near real time. So what makes them truly transformative is that it's a two-way communications capability, which means unlike the old meters that only record consumptions, the smart meters allow utilities to send information back to the consumer, right? Whether it's pricing updates and also demand response signals. We're going to talk about that in a moment, or alerts. So this interaction is foundational for creating a smart and responsive grid. So keep that in mind. So from billing perspective, smart meters, they enable time of use, which is TOU, tariffs, and a lot of inverters today, they even have that features, time of use, where the price of electricity varies depending on the demand and the time of the day, because they are peak time and off-peak time. So this encourages consumers to shift the usage away from peak hours, which then help to flatten the demand spikes and reduce stress on the grid, right? So on peak time, the demand can spike very high, which might be a problem or a challenge for the power grid to actually supply that. So using smart meters, the utility can work with consumers to implement these type of demand response, but we're going to talk about that. That's ultimately flatten the demand spikes. But coming back to smart meters, they aren't just about billing efficiency, right? They offer several operational benefits as well for the utility. So which number one is the load balancing. How does it work? So by analyzing real-time consumptions patterns across regions, utility can dynamically adjust generation, manage load distributions, and even predict demand surges. So this data-driven approach enhances grid stability. And then you also have reductions of technical loss. What do I mean by technical losses? So smart meters, they aid the early detections of fault and irregularities or even energy theft. So this minimizes the loss that would otherwise go unnoticed with conventional metering. So it's that kind of added features it gives to the grid. Then there's also renewable energy integrations, right? Now, this point is very important, so please pay attention here. So as more households install solar panels or other distributed energy resources, DERs in short, Smart meters then help track the surplus energy that's being generated by these houses, and then it sends it back into the grid, enabling better coordinations of distributed generation, right? Isn't that a great thing? Okay, instead of just relying on a centralized power source, now you have all these other power distributed generation that's contributing to the grid. So for consumers, smart meters, they offer transparency and control. They can monitor their usage patterns in real time through apps or web portals, and they will identify which appliances are driving up the electricity bill and make informed decisions to reduce consumptions. That's great. And additionally, many programs now incentivize consumers to participate in demand response events, where they get rewarded for reducing usage during critical grid stress periods, peak time. Okay, now, so looking at the bigger picture, smart meters are a critical building block for the future of energy management, where homes, businesses, utilities, they basically collaborate to create a flexible, efficient, and sustainable energy ecosystems. And they also pave the way for smart homes and IoT integration, which is one of the major topics, right? We get to that, where devices can automatically adjust energy consumption based on grid conditions or user preferences. So you don't have to manually go and shut down something, so it will already have all that kind of information and preference, so automatically things get adjusted. Isn't that great? So in short, smart meters are not just devices, they are gateways to a smarter, more interactive and resilient power grid. Now let me just have a sip of my coffee here. Okay, so earlier I mentioned about the demand response a lot while talking about the smart meters. Let's quickly elaborate about these demand responses, DR, which forms part of the SCADA systems. So this is truly a game changer in modern grid management and a crucial piece in the puzzle of making our energy system smarter and more sustainable. So basically, what is a demand response, or DR? Now, at its core, it means that the power utilities will encourage or even automate the reduction or shifting of electricity usage during period of peak demand, right? Now, this isn't just about asking people to switch off their lights or their geyser during those peak time. This is about creating a dynamic interaction between consumers and the grid to optimize energy use in real time. Now, think about it. Instead of the power utility sending communication through radio waves and networks and things like that, media, to communicate these kind of messages to optimize the grid, now it has this demand response system that actually dynamically integrated. So that's actually what we're talking about here. Now, why is the demand response so important? You already guess why, right? Now let's just mention it quickly. So power grids are designed to handle peak loads. Okay, they're supposed to handle peak loads. So if you know that the particular area that you're supplying power, they've got a base load of, let's say, 1 megawatt, but sometimes it can jump to 1.5 megawatt. I'm just giving numbers, which means the power system, the utility, must be able to handle that. So it must have the capacity to go at that 1.5 megawatt at a given time, but it cannot sustain it, right? So those rare moments when electricity demand surges, like hot summer afternoons where air conditioners are blasting everywhere, or very cold winter where everyone is switching on the heater, right? But here is a catch. These peaks often occur for just a few hours in an entire year, right? So which means building and maintaining infrastructure such as pickup plants, transmission lines and substations to handle these infrequent spikes is incredibly expensive and inefficient. So instead of ramping up supply to match peak demand, utilities are now shifting towards managing the demand side of the equations, right? So instead of me responding, I will manage that side of it so that it does not catch me on this side. So this is where demand response steps in. So by incentivizing or automating consumption reductions, utilities can effectively flatten the demand curves, minimize strain on the grid, and avoid costly infrastructure upgrades. So hence we've got two main types of demand response that emerges. The first one is price-based DR. Now in this case, electricity prices, they fluctuate based on real-time demand. During peak hours, prices go up, encouraging consumers to reduce or shift their usage to off-peak times, right? Now this model is becoming more common with time of use tariffs and real-time pricing schemes. Then we also have incentives-based DR, which means utilities will offer direct financial incentives. It's almost like a payback to consumers who agree to reduce the electricity usage during critical periods. Now, this could be in the form of rebates, bill credits, or even participation payments for large industrial consumers, things of that nature. So the role of smart technologies in this case then help to drive the success of the demand response heavily, which relies on smart appliances, smart meters, and home automation system that can react instantly to that demand response signals. Because remember, it's the systems that controlling them. So these devices then create a seamless interaction where consumers, they don't have to manually intervene every time there is a demand response event. For example, a smart thermostat can automatically adjust temperature settings by a few degrees, right? Barely noticeable to the occupant. But that slight adjustment is significant for the grid balance, right? Another example would be an electric vehicle or EV chargers that can delay the charging cycles, right? Which then will help prevent that sudden load spike when thousands of EVs are plugged simultaneously right, to start charging. Then you also have, as an example, let's see, an industrial facilities, right, that can temporarily reduce non-essential process. You got all sort of machinery running, right, or lighting and things like that systems. So we start impacting core operations so they can like temporarily put them off while the core functions of the industry, the facility is moving forward. So the benefits of this demand response will then include it lower the stress on the grid, which means by reducing demand during critical times, utilities can maintain grid stability, right, and avoid blackout or blown out, also known here in South Africa as load shedding. And number two, it will also reduce the reliance on pickup plants, which is not so sustainable, right? Whereby the pickup plants, which are very expensive and often powered by fossil fuels, are only used during peak demand, reducing the need for these plants in both economically and environmentally beneficial sense of things. So one example of bigger plant would be the pump storage, hydraulic power generation, whereby they'll pump water right during the day. They'll pump water during the day, and then they will release it during the evening when there's peak demand. So they're basically assisting the grid for extra generations as that water is being released down, right? Things like that. Now there is also cost savings for everyone, and who doesn't like saving? Okay, so by avoiding infrastructure expansions and optimizing grid efficiency, utilities can then pass these savings to consumers. Additionally, consumers who participate in DR program, they directly benefit through reduced bills or financial incentives like we've mentioned earlier. So, and the last point will be enabling renewable integrations. So in demand response, it is key for that integrations of variable renewable energy sources like solar and wind, which will help balance the demand response by plugging back those into the grid. So the bigger picture, right? The bigger picture here is that the demand response transformed the traditional one-way flow of electricity from the power plant down to us consumers into a dynamic interactive energy ecosystems where consumers, us, we are not just passive users, but we are active participants in maintaining, ensuring that there is stability in the grid. So it's a shift towards a more flexible, resilient, and sustainable energy future. Let's now talk about the link. What bonds everything? Basically, the communications. How does all of them interact with one another? This is where we talk about the power line communications, PLC. So basically, all these systems that we've been talking about just now, SCADA, smart meters, demand response, they don't operate in isolation. They rely on robust, secure, and highly responsive communication networks to function seamlessly, right? So in a smart grid environment, data needs to flow constantly and securely between millions of devices, utility control centers, and edge devices. We are not forgetting the cloud platforms, right? So this communication infrastructure is the nervous systems of the modern power grid. If it's collapsed, then that's what you've heard about the terms the power grid collapse or blackout. Now, let's break down some of the key technologies making this possible. Number one, first on the list is the fiber optics network. Now, fiber optics are the backbone of high speed, right? High capacity grid communications. That's why nowadays high speed internets, they are fiber systems. Now, especially at the transmission level with massive bandwidth and ultra low latency, meaning very fast, fiber basically ensured real-time data exchange between control centers, substations, and key grid assets, and it has immunity to electromagnetic interferences, which actually makes it highly reliable in high voltage environments. And number two on that list is the wireless network, your 4Gs, 5G, and Wi-Fi systems, right? The LoRa, wide area network. Now, wireless technologies, they very much indispensable. We can't do away with them, right? Especially in distributed grids, remote areas, and urban zones where laying cable isn't practical at all or very cost effective. So it's very expensive. So which means 5G brings ultra reliable, low latency communications, crucial for real-time grid control. Then you've got the LoRa wide area, which is the long-range wide area network. It's very ideal for long distance, as the name implies. Low power communications as well. So this is a very good, perfect for remote sensors and smart meters in villages and rural places where the grids need to access. Wi-Fi is then often used for localized communication, such as within smart homes or campuses. Like, for example, I've done tutorial about IoT integrations of controlling some equipment, but the Wi-Fi is a central system that makes that everything to tick, right? If you cut off the Wi-Fi, everything falls away. So power line communications, or PLC, which is number 3 in this list here. So the PLC basically leveraged existing electricity distribution lines to carry data signal. Okay, so that's why the name implies power line communications. So it provides very cost-effective solutions for a last mile connectivity, as we know it, as it is called. So particularly to homes and small businesses, while the bandwidth is limited. Now this power line communication system has a bandwidth limitation compared to fiber, but PLC, make no mistake, is excellent for applications like advanced metering infrastructures, or AMI, and simple control signal. Then we have mesh networks. Now, mesh networks are essential for ensuring networks resilience and scalability, especially in smart metering. In this case, devices like smart meters, they will communicate with neighboring devices, forming a self-healing network, like relaying messages. Now, if one path fails, the data will then reroute, right, through alternative path, ensuring continuous connectivity. So it's a very critical feature for AMI rollouts in dense urban environment, advanced metering infrastructure. Now, one example of a mesh network which you can actually implement using ESPs, you can use multiple of ESP devices, whether it's a 32 or 8266 family. You can use them in a way that they can form a large mesh network, couple of meters, maybe kilometers, but it becomes very complex to maintain. Then you've got edge computing or cloud integrations. Now, with enormous amount of data being generated, it's impractical to send everything back to central servers, right? So this is where edge computing step in, which basically allows real-time data processing close to where it's being generated at a substation. So we've got field devices, or even within smart meters themselves, right? These reduces latency and improve systems responsiveness to the type of data that's being released by sensors. So on the other side, the cloud platforms provides the heavy lifting for data storage, advanced analytics, and machine learnings, basically enabling utilities to collect demand patterns, detect anomalies within systems, and optimize grid performance on a large scale. Those are the key aspects of how these communications network, these infrastructures are maintained, and what makes the major point that tie all of them together. But connectivity brings new challenges. Make no mistake about that. Okay, this is where cybersecurity becomes very critical. Now, as we integrate millions of connected devices into the grid, like I've mentioned earlier, cybersecurity becomes just as critical as the physical grid security itself, like putting a security guard in front of a substation to make sure no one goes in there and go commit a sabotage. That's physical security. But cyber security, to protect that network that we just described, become as critical. So these communication channels are potential entry point for cyber attacks that could actually disrupt operations, steal sensitive data, or even threaten the national grid stability, cripple the whole grid itself. So securing the grids basically involve encryption of data in transit and at rest, multi-layered network segmentations to isolate critical control systems. Then you've got real-time intrusions detections and anomaly detection systems. And we also have regular vulnerability assessment and patch management. So in a sense, smart grid must be designed with security by design principle, which basically ensure that every device, from a field sensor to a cloud server, right in between, they operate within a secure and trusted environment. Because just imagine, in absence of that cyber security systems during a time of war, you've got an opposing country that infiltrate your grid and sends cyber attacks to basically cripple and shut down your entire grids. Now how chaotic would that be for a country? This is why cybersecurity becomes very important for the national grid. So basically, to wrap up these conversations about SCADA systems, smart meters, demand response programs, and the robust communication network that we just described. So these 4 pillars, they're making the power grids very smart, more reliable, and obviously more sustainable. So the future is moving towards a grid where consumers are not just passive users, but very much active participants in generating, storing, and managing their own energy with the use of solar energy distribution generators. And as engineers, it's our job to design systems that support these decentralized data-driven energy landscape. So in the next episode, we'll take these further and discuss how distributed energy resources, or DERs, like the rooftop solars who are popping up all over the place, wind turbines, and battery storage, how they are reshaping the grid dynamics. Now, if you've really enjoyed this episode, please make sure to subscribe and share it with fellow engineers or tech enthusiasts. You can reach out for questions or topic suggestions in the comment sections, or you can send me a tweet using at CMTEQ on the X platform. So thank you very much for your attention. I hope it has been very useful. Don't forget to give it a thumbs up and subscribe to CMTEQ channel. Until next time, stay wired, stay grounded, and keep learning. Cheers.